For these critics, the decoherence problem is not just a minor hurdle for OR, it is honestly a fatal flaw. Therefore, any defense of the quantum mind has to provide a compelling answer to this challenge. It's not enough to have a beautiful theory about gravity and consciousness. You also have to explain how the biological hardware could possibly protect its quantum operations from the relentless onslaught of decoherence. The theory needs a shield. It must propose a plausible biological mechanism by which microtubules can isolate their quantum computations from the warm, wet chaos surrounding them, preserving their coherence for timescales that are orders of magnitude longer than physicists would normally expect. The entire viability of the OR model really hinges on this crucial biological detail. The proponents of OR have not ignored the decoherence challenge. Stuart Hameroff and his collaborators have actually put forward several counter-arguments and proposed mechanisms that could, at least in theory, fend off the thermal noise of the cell. Their primary defense centers on the specific structure and environment of the microtubule itself. They argue that the initial damning calculations made by critics like Tegmark were based on oversimplified models that just didn't capture the true biological complexity of the system. The microtubule, they contend, isn't just a passive structure floating in the cellular soup. It's a highly organized and potentially shielded environment, uniquely suited for protecting quantum states. One key proposal is that the tubulin proteins within the microtubule lattice do not act independently, but in a collective, synchronized manner. The superpositions might be distributed across many tubulins in a way that makes them more robust to local disturbances, a concept known as collective excitation. Furthermore, they suggest that the interior of the microtubule cylinder might be filled with a special, ordered form of water. This ordered water, they claim, could act as an insulating sheath, creating an electrically isolated channel down the core of the microtubule, shielding the quantum states within the tubulin proteins from the noisy electrical fluctuations in the surrounding cytoplasm. Another part of the shielding hypothesis involves the very speed of the proposed quantum computations. Hameroff suggests that the processing within the tubulins could occur at extremely high frequencies in the gigahertz to terahertz range. This would mean that many computational steps could take place before decoherence has a chance to set in. The idea is that the quantum state is processed and built up so rapidly that it basically outruns the environmental noise. They also point to the discovery of quantum effects in other warm, wet biological systems, such as photosynthesis, where quantum coherence plays a demonstrable role in energy transfer, proving that nature has found ways to protect quantum processes from decoherence. These counter-arguments transform the debate from a simple yes or no into a far more nuanced discussion about the precise biophysics of the microtubule. Are microtubules truly capable of this level of shielding? Is water inside them ordered in a special way? Can tubulins act in a coherent, collective manner? These are now open, empirical questions that can be investigated through advanced microscopy and biophysical experiments. While the shielding hypothesis remains controversial and is, honestly, far from proven, it provides a plausible, if speculative, path forward. It suggests that we really shouldn't dismiss the possibility of quantum computation in the brain based on simplified models alone. The intense debate over decoherence in the brain really highlights a fundamental difficulty. Biology is messy. When testing a theory like OR, which combines a claim about fundamental physics, objective reduction, with a claim about biology, namely quantum processes in microtubules, a negative result is always ambiguous. If our mass invariance test fails to show a frequency shift, does it mean the physics of OR is wrong? Or does it simply mean that decoherence is too strong in microtubules and the biological part of the theory is wrong? It would be immensely valuable to find a way to test Penrose's physical prediction, the gravity-induced collapse, in a clean, controllable system, completely separate from the complexities of the brain. And, actually, this is precisely what physicists in the field of optomechanics are now attempting to do. They are designing experiments to probe the boundaries between the quantum and classical worlds using non-biological systems. The goal is to create and sustain a quantum superposition of a macroscopic object, an object large enough for its gravitational self-energy to be significant, and then watch to see if it collapses on its own, just as Penrose predicts. If they can demonstrate that tau equals h bar divided by Eg holds true in a vacuum chamber on a lab bench, it would lend tremendous credibility to the physical foundation of the OR theory, regardless of whether it ultimately happens in the brain. These experiments often involve using lasers to trap and cool a tiny object, such as a nanoparticle or a microscopic mirror, down to near absolute zero. By cooling it, they remove the thermal vibrations that would cause decoherence. By trapping it in a vacuum, they isolate it from collisions with air molecules. Once the object is perfectly still and isolated, the next step is to use quantum tricks to place it into a spatial superposition, a state of being in two different locations at once. The separation distance might be tiny, maybe only the width of an atom, but for an object containing billions of atoms, this is a massive superposition with a significant gravitational self-energy, e.g. The stage is then set for the crucial measurement. According to standard quantum mechanics, this superposition should last indefinitely as long as it is isolated. But according to Penrose's objective reduction, it has a finite lifetime, tau, determined by its mass and separation. The experiment is designed to hold the superposition and simply wait, watching for the moment it spontaneously collapses. By repeating this with objects of different masses and different separation distances, physicists can check if the collapse time scales exactly as the Penrose equation predicts. This provides a direct, biology-free test of the core physical claim that underpins the entire quantum consciousness hypothesis. Let's imagine one such tabletop experiment in more detail. A team of physicists uses a focused laser beam, an optical tweezer, to levitate a tiny silica nanosphere, about 100 nanometers in diameter, inside an ultra-high vacuum chamber. They use other lasers to cool the sphere's motion until it is almost perfectly still, reaching a quantum ground state. At this point, they apply a carefully timed pulse of light to split the sphere's quantum state, placing it into a superposition of being in two slightly different positions simultaneously.